All right, guys, so we're going to do our notes today on the Lewis structures of molecules. Remember that molecules are only covalently bonded things. So covalent things that have non-metals with other non-metals. All right, that's what makes something a molecule, non-metal bond being covalent. Okay, so when these covalent molecules come together, they are sharing electrons. And when they are sharing their electrons, they have to share in different ways to try to make every element involved in that bond as stable as possible. So they have to share in different ways and different amounts that will make them all as stable as possible, trying to get them as close to that 8-octet rule, having 8 valence electrons as they can. And it makes all these different shapes. And this is your little box of shapes right here. The ones that you're actually going to be tested on is linear, trigonal planar, bent, and tetrahedral. But you can kind of notice there is other ways to be bent and a few other ways to be linear as well. Okay. And there's other shapes, just those are the ones that we're going to focus on in this class. So let's begin. So when we're starting, I just want to talk about the 3 types of bonds in between these first. So when we draw them, the dashed line in between always represents a pair, so 2 electrons, okay? So when I have F2, so I have 2 fluorines bonded to each other, okay, like this, and we draw them bonded together like that with the dashed line. Those dashed lines actually mean 2 electrons, okay? Now, I'm going to kind of speed through this part and we're going to break down how I know how these are bonded later. But in fluorine, they end up having basically a filled outer shell to the best they can, of being with them sharing these 2 in the middle, like that, in a single bond. So this is a single bond. There you go. Okay, so here we go. A single bond. Now, sometimes they have to share more than just one time to make themselves stable. They have to do more sharing so that each atom gets that octet. So for example, we have oxygen, O2, when it bonds to itself. So oxygen with oxygen like this. Okay, but actually what happens in oxygen is it ends up needing to share 4 electrons. So each of them sharing 2. To make themselves happy. And then they end up having 1, 2, 3, 4, 5, 6, 7, 8. So this oxygen is 1, 2, 3, 4, 5, 6, 7, 8 when it's sharing. And this oxygen also ends up like that. So this is what's called a double bond, made of 2 shared pairs of electrons. And then lastly, we have a triple bond where it has 3 shared pairs. So when nitrogen bonds to itself, like this, it actually, to make itself stable, actually has to share 3 electrons each. So 6 electrons are being shared between them, like that, and they end up having 2 over here. So nitrogen has 1, 2, and has access to 3, 4, 5, 6, 7, 8. Same thing for the other nitrogen. So everybody's having that 8-octet rule. So this is a triple bond. And triple bonds are the strongest. Okay, so obviously harder to break 3 bonds than it is to break 1. Okay, now, as you're kind of seeing me put all these like dots around it, that all comes back to our Lewis dot structures that we've been working on before, where how many dots I know it gets is I find its valence electrons here. It kind of comes from that starting point of knowing how many valence electrons they have and moves forward. So we're going to kind of start putting all these pieces together to know how to build these shapes. Now, you have this list of rules, and you'll always be given these rules. You don't have to memorize these rules. You just have to know how to use them, okay? So it's pretty wordy, so I'm going to kind of add some special things off to the side and show you how to go through them. Basically, you just always start with rule 1 and work your way down until the shape is built, okay? So here we go. For today, we're only going to do these first 3, and then you're going to do 3 problems on your worksheet that are also underlined, okay, that kind of will match these 3 vibes, okay? All right, so it says, the structure of a molecule can be determined by using the valence shell electron pair repulsion theory, or in short, VSEPR. So we're learning how to do these rules of how to know how to draw the shape of a covalent molecule, using VSEPR. Okay, so the first number rule says add the total number of valence electrons. So that's pretty much big main rule number 1. Add up your total valence electrons for all the atoms in the compound to determine the number of pairs you'll need. Okay, so here we go. This will matter later that if we have, if it has a charge, but we'll talk about that tomorrow when we actually have one that has a charge. I'm not going to talk about that today. Okay, so what we're going to do is we're going to figure out how many valence electrons carbon has and how many valence electrons chlorine has. So carbon is up here. Okay, so carbon's right here in the 4th column. Whoop, there you go. So in that 4th, or really 14, but we remember we pretend the teens aren't there, and it's just the 4. So it has 4 valence electrons. Okay, so we're starting with 4 valence electrons for carbon, and then chlorine is somewhere over here. I'm not exactly sure where, but it's somewhere over here in the 7th column. Okay, so it has 7, but there's 4 of them. So 7 times 4, like that. Okay, so 7 times 4 is 28, and plus 4, so we have 32 valence electrons to work with. I'm writing VE. You can write it out, valence electrons, if it doesn't make sense to you to remember that, but I write 32 VE for 32 valence electrons. So that's my check 1. I did my rule number 1. Counted up my valence electrons. I have to use all 32. They have 32 to share of their valence electrons. Okay, number 2. Arrange the peripheral. Okay, that's a big word. Peripheral means outside. Okay, so arrange the outside atoms. So not the one that's going to go in the middle, the ones on the outside. So arrange the outside atoms around the central atom, placing 1 electron pair. Remember, it's represented by a dash between each. So basically, you're going to put an atom in the center. You're going to bond it to all other atoms using a dash that represents 2 electrons, and we're going to make sure that we subtract the total electrons used from this process. That's very important. It's one of the biggest things I see kids not do, is they just forget to keep track of their subtracting them off, and then they don't know how many electrons they've used. They don't know how many they have left. Okay, so how do I know which one's going to go on the center? Basically, a kind of rule of thumb is if you have carbon as a choice, it goes in the center. Okay, so carbon loves to be in the center. Other than that, hydrogen will never go in the center. Okay, and beyond that, the one you have one of. That's kind of how I remember it. Usually it's the one you have one of. That's the one that goes in the center. Okay, so if I'm looking at carbon and chlorine, there's 4 of them. So using my carbon rule, carbon always likes to go in the center. It's going to go in the center. But also using the fact that the one I have one of goes in the center. Carbon is the one I have one of. I have 4 chlorines. So I'm going to put carbon in the center. And then I'm going to put that dash representing the bonds to all the rest of the atoms, which is 4 chlorines. So 1, 2, 3, 4. And I'm going to show it bonding to those 4 chlorines. Like that. Oh no, almost dropped my pencil. This needs to move a little bit up. You're not going to be able to see my dots. So 7 times 4 equals 32 valence electrons. Okay, like that. So now, right now I've used, remember each dash represents 2 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. So I've used 8 electrons though so far. I'm going to kind of write it over here to the side. So 32 minus 8, 30, I need to take another 6. We got 24 valence electrons left. Okay, so 24 valence electrons left that I still got to use. So we've done this rule, check, but now I need to keep going until I'm out of electrons. So use the remaining electrons. So use all the remaining electrons to fulfill the octet rule. Remember, everything wants to have 8 valence electrons, so 8 outer shell electrons on each peripheral. Remember, peripheral means outside atoms. So we're going to make sure that all of our atoms on the outside have 8. with our leftover electrons. So right now, chlorine right here is an outside atom, has access to 2 electrons because it's sharing one. So it has access to 2 electrons. So it needs 6 more. 1, 2, 3, 4, 5, 6. Okay, same thing for all the other chlorines. So I already had 6. So this would be 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I just used 24 electrons to make them all stable, and I had 24 electrons left. So subtract that off and end up with 0. So now we're done there. We've checked it. We've used up all our valence electrons. Okay, so we've done that. Check. Now I go to number 4. If any electron pairs still remain, place them on the central atom. I don't have any electrons left, so I'm skip that step. Check to make sure that all the atoms have an octet. If some atoms do not, then we'll have to make a double bond or a triple bond. So let's check. Carbon has access to 1, 2, 3, 4, 5, 6, 7, 8. It has access to 8 electrons. It's stable. And all the chlorines, we made sure, had access to 8 because 1, 2, 3, 4, 5, 6, access to 7, 8. Okay, so they're all good. And then elements with atomic numbers lower than carbon, these are just kind of like extra rules. So really, if you're here and all the atoms have a fulfilled octet, then you're finished. So this